how do we measure the exact length of a complex, continuously curved path as it twists through space? The standard Euclidean distance formula calculates the gap between 2 points in a straight line. But as a path begins to curve, that direct calculation fails to capture the distance traveled. This discrepancy between straight distance and curved length troubled early geometers, eventually requiring the tools of advanced analysis to resolve. We find the rigorous mathematical solution in Walter Rudin's Principles of Mathematical Analysis. The formal derivation is contained in Chapter 6, under the section for Rectifiable Curves. We are going to unpack Rudin's specific framework for defining and computing curve length from first principles. To prove the properties of these paths, we must look past our geometric intuition and rebuild the concept of a curve from logic alone. Rudin establishes this framework in definition 6.26. Note the phrasing of the definition. Rudin defines the curve as the mapping itself. This requires us to distinguish between the one-dimensional parameter interval and the multi-dimensional space it maps into. We define a continuous mapping, gamma. As our parameter t moves along the interval from a to b, gamma of t traces the actual path in space. If the mapping is strictly one-to-one, Rudin defines the path as an arc. If the path loops back so the start and end points are identical, the curve is closed. By focusing on the mapping, we can distinguish between paths that share the same shape but are traversed at different speeds or in different directions. Defining a curve as a journey through time, rather than a static set of points, provides the structure necessary to calculate its length. While we can determine the length of a straight vector, we have no direct way to measure a continuous bend. To resolve this, we introduce a partition, P, which divides the parameter interval into a finite number of steps. These partition points are then mapped directly onto the spatial curve. By connecting these points with straight segments, we create a polygonal path that approximates the curve. The length of this specific approximation is the sum of these individual segments. The magnitude brackets calculate the distance between 2 points, and the sigma sums every segment in the partition. Because a straight line is the shortest path between any 2 points, this polygonal sum is always less than or equal to the actual length of the curve. As we refine the partition by adding more points, the jagged path begins to converge on the smooth geometry of the curve. By summing these discrete segments, we translate the continuous path into a measurable total. This leads to a theoretical limit. What is the result if we evaluate every possible partition of the interval? Rudin defines the total length of the curve as the supremum of these polygonal sums. The supremum is the least upper bound. As partitions become finer, the calculated length increases toward a specific mathematical ceiling. If this supremum is finite, we say that the curve is rectifiable. Continuity alone is not enough to ensure a path can be measured this way. Certain continuous curves bend so frequently, at every conceivable scale, that they actually possess an infinite length within a bounded space. The supremum allows us to categorize paths where length is a well-defined, finite property. Theorem 6.27 connects the supremum to the mechanics of the derivative. The theorem applies when the derivative of the mapping is continuous on the interval. Here, total length is precisely equal to the integral of the magnitude of the derivative. As the partition segments shrink toward zero, the straight lines between points become tangent velocity vectors. Through the mean value theorem, we can convert the discrete steps of the partition into the continuous differential of an integral. Because the derivative is uniformly continuous, the approximation error disappears entirely as we take the limit. Theorem 6.27 allows us to compute an abstract supremum using the practical tools of the Riemann integral. This fundamental logic provides the precise, rigorous definition of length required for analyzing curves on more complex manifolds. In physics, this allows us to calculate the distance a particle travels by integrating its speed over time. In fields like engineering and computer graphics, the concept of rectifiability ensures that complex digital models have precise, physical, measurable dimensions. To summarize, we analyze curves as parameter mappings rather than static sets. We define true length as the supremum of all possible polygonal approximations. And when the mapping is continuously differentiable, this supremum resolves into the Riemann integral of the velocity. Understanding rectifiable curves allows us to measure nonlinear paths with the same precision we apply to straight lines. If you want to see more deep dives into the theorems and proofs found in classic texts like Rudin, like and subscribe to continue your study of higher mathematics.